Alrighty, here we are, ladies and gentlemen, with some fresh IB chemistry flipped classroom. And this is about galvanic cell potentials. It's how we're calculating the voltage of stuff. This goes along with a page in your workbook that you could probably figure out which one it is. It's a note page. It's like fill in the blanks. You also need your data booklet. This page right here, table 24. So why don't you gather those things up before you proceed. So we've talked about redox, we've talked about electrons changing places, we've talked about oxidation and reduction. So sort of analogy or a way you can think about redox is kind of a battle for electrons. And you know, we hate to think of electrons as having a motive or whatever, but some elements are good, or some species are good at taking electrons, others are good at giving up electrons. So we can sort of imagine an imaginary mountain, and those things that want to most give up electrons are at the top of the mountain. And those things that most want to take electrons are at the bottom of the mountain. And things flow downhill from the best givers to the best takers. They cannot flow uphill on their own. So electrons are going to go from essentially from a higher energy state to a lower energy state. And that's the direction they're going to want to tend to go if they can. And they can't go uphill without help. The farther apart two electrochemical species are on this mountain, the bigger the electropotential energy difference between them. And there's a force here that can be used to do useful work, which is called the electromotive force. Now, to understand what we're going to talk about here, we have to talk a little bit about electricity in general, and we need to at least know the bare bones terms that are involved with electricity. So you hear volts very often, you hear amps or amperes less often, but you definitely hear volts. Volts are the measurement of electric potentials, and amps measure current. So these are two very different things. An analogy that you might have is a waterfall. So the height of that waterfall would correspond to the voltage. So a very tall waterfall with a thin stream of water, that's high voltage, low amperage. That's something like a static electric shock that you get when you touch a doorknob or whatever. Those can have actually extremely high voltages, but very low amperages. A small waterfall in the midst of a raging river, that's like low voltage but high amperage. Amperage has to do with how many electrons are flowing, or how much water in this analogy. When it comes to deadliness of shocks, it tends actually to be the amps, not the volts, that's more dangerous. What volt implies is that 1 joule of work can be done per coulomb of charge. Coulomb is a unit. It is the amount of charge in 6.42 times 10 to the 18th electrons. There's a slight change there to your little answer sheet or your note sheet. A coulomb is the charge on 6.24 times 10 to the 18th electrons. So 1 volt means that a joule of work can be done by that that quantity of charge, I guess, or of electrons. So and then an amp, like I said, that has to do with how many electrons are flowing. An ampere is about 1 coulomb per second. So if a current is flowing along at 1 amp, that's 1 coulomb of charge passing along in 1 second. So, you know, just to relax your mind and give you a little bit before we go any further, a couple of waterfalls here. This is Lava Falls, which is part of the Colorado River, which goes through the Grand Canyon. A huge amount of water passes over it. This is, I don't know, some falls in Hawaii, but it's, you know, nice and tall, but thin. At least from this distance, it looks thin. So here we've got high amperage, low voltage. Here we've got high voltage, low amperage. I actually I rafted through the entire Grand Canyon about 6 or 7 years ago now. This is what Lava Falls looks like. This is me right there. No, I don't think it is, but I rode through on a raft just pretty much exactly like this. So if this was a picture of me, it would have looked a lot of something like that, except I was in the front here when I really did it, now that I think about it. But yeah, I did that a few years ago. It was awesome. So we talked about galvanic cells. We talked about hooking them together and all that stuff. We talked a little bit about voltage. When you hook up two half cells, again, the force is called the electromotive force. It's when we calculate them, like we're going to be doing in a second, that's a theoretical maximum. It ignores things like resistance in the wires. Every time we hook things together with wires and other stuff, there's resistance. So all that takes away from the electromotive force. So It's called a theoretical. It's called the electromotive force. It's a theoretical thing. It's the absolute maximum that you could get, ignoring resistance and all that kind of stuff. So when we do calculate these voltages, just understand that it's a theoretical maximum and not necessarily something you achieve in real life. And it is measured in volts. So the thing about voltages and electric potentials is that it's only relative. It's only relative to something else. And, we can construct galvanic cells from two half cells, and it would be useful to know the electric potential of any particular half cell for reasons we'll get to in a second. But, again, it's all relative, so you can only compare it to something else. So to solve this problem, what they did is they developed something called the standard hydrogen electrode. And you need to know a little bit about what the standard hydrogen electrode looks like and is composed of. We've talked in class about like a zinc cell, which would have a piece of zinc and zinc ions. This is a cell based on hydrogen. And how they build it, and you do need to be aware of the pieces and parts of this, is they use a platinum electrode. They use platinum because it's very unreactive. And since, unlike our zinc electrodes and zinc ions, for instance, or a copper electrode and copper ions, zinc, of course, hydrogen is a gas. So to allow this electrode to be conductive, you have to use a platinum wire, which is really unreactive. You surround it by hydrogen gas at 1 atmosphere pressure. You dip the whole business in a acid solution where the hydrogen ion concentration is 1, and you maintain the temperature at 25 Celsius, or 298 Kelvin. And when you do all of this, you have the standard hydrogen electrode, so there's a picture of it. So literally you're pumping gas in. You got a glass container around the platinum electrode to kind of hold the gas in there. So you're bubbling hydrogen gas through. You got an HCl, activity 1, just that means it's concentration, platinum electrode. So you could hook this up to something else. Like you could hook it up to a zinc electrode or a copper electrode or whatever. But the hydrogen electrode was arbitrarily assigned a voltage of 0, and then all other ones are comparison to that. Does it even say that on here? Yeah, arbitrarily assigned a potential of 0 volts. So all other potentials that you see when we look on that table I showed you at the beginning of the slide and all that stuff, they're all relative to hydrogen. So if you look at that table that I told you need to get out, those are reduction potentials. So that's just the way they list them. They're listed as reduction potentials. The more positive that value, the more likely that particular species is to be reduced. So the more positive that value, the more likely that thing that you're seeing there is to occur. So the one in your IB data booklet, lists the least likely to be reduced with the most negative charge at the top and the most likely to be reduced, like the fluorine at the bottom. Now, you could also figure out, if you want to know what the oxidation potential would be for any of those reactions, you can flip that. You could flip the reaction exactly backwards, and that flips the charge. And we'll look at some of these. We'll look at some examples a little later. And then when you're looking at two half reactions in oxidation and reduction, you find them both on the table, you flip them, and you add them together, and that's the total voltage. And again, it's easier seen by some examples, which we'll look at. The actual potential is always a bit less, as I mentioned earlier. We lose some of our potential energy to heat and other things. Reactions that are spontaneous will have positive potential differences, so they'll produce a positive voltage when you hook them together, this half cells together. So, I swore to myself I wasn't going to put any silly cat pictures on this. I don't know. This is a classic. Really, it's one of my very favorites. So I don't know. I just kind of happened to run across it. I had to put that in there. Yeah, so here we go. Here's our table of potentials. And again, the more negative this value is, the less likely this process is to occur. So lithium ions, very unlikely to be reduced, whereas fluorine, the element fluorine, loves to take electrons, so it's very likely to be reduced. And these are all reduction potentials, but we could flip any one of them to figure out what the oxidation potential would be. This note sheet is kind of in a weird order, but let's now just touch on Gibbs. Before we really delve into how to find voltages, let's see how this relates to Gibbs free energy. We remember when we learned about energetics that delta G must be negative in any spontaneous process. So there's a relatively easy equation to use to convert voltages to Gibbs free energy values. Delta G is change in Gibbs free energy. There's a negative sign there. N is moles of electrons transferred. F is the Faraday constant, which is 9.65 times 10 to the fourth coulombs per mole of electrons. So that's the charge in a mole of electrons, is what it is. And E is the cell potential, so the voltage that a particular galvanic cell can produce. And usually it's going to be the standard cell potentials. We'll talk about non-standard stuff. We don't worry about that too much right now. Okay, so you should also have a practice worksheet that's got a couple of extra problems on it. So we can solve some of these. And so it says the following has a cell potential of 1.1 volts, 1.10 volts under standard conditions. So it's telling us this reaction, if we built a galvanic cell out of this one, it will produce 1.1 volts. And it wants us to change that to the Gibbs free energy. So we can see the formula here. And so N is going to be our mole of electrons, and we're noticing that there's a transfer of 2 electrons here. The zinc is getting oxidized. It's losing 2 electrons. The Cu plus 2 ions are gaining them. So let me get my little pen here. So we've got a negative sign here. N is going to be 2 because 2 moles of electrons are transferred. And then we have the Faraday constant, which is 9.65. 0.65 times, sorry for my writing, I don't have a pen with me to write on the screen, times 10 to the fourth, and then times the voltage, which is 1.1, oh, why did it do that? 1.10, and then we have a funny line for no reason, but you know, you guys are smart. I think you can figure out what's going on here. 2 times the Faraday constant times the voltage, all that multiplied together is going to give us our delta G. You're going to get a value in joules here, and in this case, if we multiply those out, we get negative 212,300 joules. And again, random lines popping up to infuriate Mr. Lose. That's a conspiracy. That's joules. It's actually joules per mole. I would show you how the units cancel out and stuff if I didn't have a bizarre pen that's hard enough to write numbers with. But, you know, we might change it to kilojoules, you know, for like sig-fig purposes or whatever. Do it 1 to kilojoules per mole. And usually delta G is given in kilojoules per mole anyway. And this all makes sense. Oh, there's another one. Fun. It all makes sense because it's a negative delta G. The voltage is positive. That's the way it's supposed to work. Positive voltage means a reaction is spontaneous. Negative delta G means a reaction is spontaneous. And when we're building a battery, that's what we want. We want a spontaneous reaction. So let's look at another one here. Following reaction carried out at 298 Kelvin. So basically this is just another way of saying that it's under standard conditions, so we don't need to worry about that too much. It has the potential of 0.92 volts. What is the Gibbs free energy change for this reaction? All right, well, just as easy as falling off a bicycle, as my grandmother used to say. I don't know what's wrong with me. N is 3. The Faraday constant is 9.65 times 10 to the negative fourth, positive fourth rather, 9.65 times 10 to the positive fourth, and the electric potential for this particular reaction, so if we made a cell from aluminum and chromium, is 0.92. So again, we just need to multiply all those together and we'll figure out what the total overall Gibbs free energy change is. Again, it's going to give us a value in joules per mole when we do this. By my reckoning here, I got negative 266,340. And again, that's joules. which we could again change to kilojoules, negative 266,000 for sig fig purposes. Maybe 2 here, I guess. Negative 270,000 for 2 sig figs if we want to get our sig figs right. Okay, so hopefully that's not too bad. Let's see. There's one more here. Oh yes, there it is. Okay, so this one you should try on your own. You should pause the video here for a second. Try this one on your own. Look at this reaction. Take a look, a little gander at this hint. Is it balanced? Is it balanced? It probably needs to be balanced before you start this. Okay, so I think I have this solved on the next slide. Yes, indeed. So if we looked carefully at that reaction, it's balanced for atoms, but it's not balanced for charge. So we would need to, there's a few ways you could do it. But one way would be to flip it into the half, or put it into the half reactions, the oxidation half reaction, the reduction half reaction. Kind of realize that we need to balance those electrons. So what this changes is that the moles of electrons is 6, because when we actually balance the number of electrons, we realize that the least number of electrons that we'd have to transfer would be 6. The actual balance reaction would look like that. So you put the 6 in there. The voltage here, if you notice on this one, is negative, and then that ends up making our overall answer not negative, but positive. Whoops. Which all makes sense because, again, a positive delta G would mean a non-spontaneous reaction, as would a negative voltage. So for a negative voltage, we'd be expecting a positive delta G and vice versa. All right. Good fun had by all. So now that we did that, let's look at how you could calculate the voltage for galvanic cells in the first place. And when you're just calculating these, like I mentioned, it assumes 298 Kelvin, 1 molar solution, so any ions at all, they have to be 1 molar in concentration. If there's any gases, 1 atmospheric gas pressure. Any variation from that, you're not actually going to get the voltage that you'd expect. So this one is back on your little note sheet. And so let's say we had this cell right here. Now, through the magic, like on a cooking show, when they, open an oven and the thing is like already cooked or whatever, I magically make the world's best drawing of a galvanic cell appear, where we got one of those spazzy lines, but it ends up being the wire that's connecting my magnesium electrode and my zinc electrode. Here's my 2 half cells. Here's my salt bridge, etc. So suppose we wanted to know, hey, man, if I built a galvanic cell out of these things, what kind of voltage could I expect to get? We talked already about just kind of making the cells in general, but now we can actually calculate the voltage that we'd get if we measured it up here, if we wired a little voltmeter into it. So we're gonna try to figure out how to do that. We're gonna try to do the electric potential. You do need the table of electric potentials for this, reduction potentials. We'll figure out which the anode and the cathode and all that good stuff. And then yeah, there's another one there. Okay, so let's do this one first though. We're going to again, we're going to figure out what would be the actual voltage if we built that wonderful cell that I drew on the previous one. So we're going to split it into the oxidation and reduction half reactions. So the magnesium is getting oxidized because it's going to Mg2+. And then we've got 2E- over here. And then we've got the zinc ions, which are getting reduced. So we've got Zn2+ ions. Nice. And we've got electrons there, and we're forming zinc. So there's my oxidation half reaction, there's my reduction half reaction. And we're going to split up our cells, so these are happening in 2 separate cells. Anyway, we are now going to calculate the cell potential. So to do that, I need to find the potential of each of these half reactions up here. So remember, the table is a table of reduction potentials. So this top reaction, I'm not going to find that reaction, but I'm going to find the opposite of that reaction on there. So if you look in your table of reduction potentials, part of the way down, you'll see, again, not this reaction, but the exact reverse of it. And you'll see that its reduction potential is negative 2.37. But I have flipped it. I'm writing it in the opposite direction, so therefore that flips the sign. So the voltage of this process, the way I've written it, is positive 2.37 volts. This one, we can find this one on the table of reduction potentials just like this. Zinc ions getting to electrons going to zinc. So its potential is negative 0.76. And so I'm looking up each of the two half reactions that add to this overall reaction. The sum of the voltages of the half reactions are the voltage of the actual overall reaction and of the cell that you might build from these things. So the overall reaction is those two things summed up. That's positive 1.61 volts. And so yes, this is a spontaneous reaction in the direction it's written because it has a positive voltage. What is the anode and the cathode? Well, a couple ways we could think about this, but remember CPR, cathode reduction positive. So the magnesium electrode is going to be my anode. It's going to be Mg because that's where oxidation is taking place. And my zinc electrode is going to be the cathode. So we got the magnesium and magnesium ions over here, the zinc and zinc ions over here. Magnesium is my anode, zinc is going to be my cathode. So yeah, this just reiterates some of the same stuff that we just looked at here and that I went through, but you got to see it in sloppy red writing instead of this. I think you're a greater person for it, probably. Yep. Okay, so a different reaction here. So let's do the same thing, except with this reaction. Okay, so I started to draw this. I tried to draw the cell and it was so bad I just quit. So anyway, I think you get the idea. We got a magnesium cell, we got an aluminum cell. This is our reaction. So we're going to split this into the oxidation and reduction half reactions. The magnesium is getting oxidized. It's going to Mg2 plus 2E minus. And the aluminum ions are getting reduced. Maybe, I don't know. I got an idea about why it's doing that. Whoops, 3E minus. And that's going to aluminum. Okay. So notice our electron gain or loss is not equal here. We're losing 2 electrons and we're gaining 3. So we would need to balance them. Now check this out though, kids. We would want to multiply that whole thing by 3. And then we'd want to multiply this whole thing by 2 to balance the electrons. But you know what? I'm not actually going to do it. I'm not actually going to carry through and multiply them out and actually balance it. Here's why. What's kind of surprising is we can find, well, for example, this aluminum. We can find this on our table of reduction potentials. And you would think that when you multiply by 2, you should multiply that voltage by 2. But do not! Do not do it. That's why I'm not going to actually go ahead and multiply it out. I'm doing this just to show anyone who looks like, hey, fella, I was thinking. I knew that these electron gain or loss wasn't balanced. So when I write the half reactions, I am showing that I know that to balance the electrons. But when it comes to actually figuring out the voltage, you do not actually multiply the voltages by 3 and by 2. What I will do, though, is, so I'll do this one first. This is a reduction. You should see this exact reaction on your table of reduction potentials. The potential there for the bottom one is negative 1.66. And this is the one we already looked at. Again, you will not see this oxidation, but you will see the exact opposite. You'll see the reduction. It's positive 2.37. And again, I am not multiplying this by 2, and I'm not multiplying this by 3, I'm not multiplying this by 2, I'm just adding them up exactly like we did in the last one, and it's 0.71 volts. And there we are, happy as can be that we've calculated this voltage correctly. All right, let's see what's next. I don't know about you, but I can't wait. Oh yes, the same thing again, but not in sloppy red pen. Maybe that's a good, because that last one was really sloppy. So half reactions, they're balanced. I did again. Again. So if this was a test and you were asked to do this, you should totally do what I'm doing here to show the person who looks that you're aware that they need to be balanced. But then do not go ahead and multiply those voltages out. And it is positive, it's spontaneous. By the way, remember when we calculated the Gibbs free energy of this, it was like this, but the opposite, and it was non-spontaneous. If you go back and look at that, magnesium is the anode because oxidation at the anode, reduction at the cathode. So my magnesium cell is the anode, my aluminum cell is the cathode. So why is it, you ask? Why is it that when when you have to change the coefficients, like we were doing on the last slide and all that stuff, like when you have to multiply this whole thing by 3 and this whole thing by 2, you'd think you'd multiply those. Why don't you? Delta G is an extensive property. In other words, it depends on the amount of stuff that you have, as is delta H. If you burn more fuel, you get more energy. If you burn less fuel, you get less energy. Same thing with delta G. So it's an extensive property that depends on the amount of stuff that you have. Potential, however, does not. Electric potential does not depend on the amount of stuff that you have. It's an intensive property like density. Things that, a small piece of gold and a big piece of gold, they both have the same density. So if we add coefficients and we double the amount of ions involved in the thing, you are going to double the delta G, because delta G is extensive. So, if we rearrange this term a little bit to solve for E, if you double the amount of stuff, or multiply it by any factor at all, you double that value right there. You do double the delta G, but you also change N by the same factor. So whatever you change this by, when you change the coefficients, or you multiply by something, you change this by the exact same factor. So solving for E here, electric potential is going to remain unchanged. Boom, math. Okay, so this is getting long, but it is mercifully almost over. Suppose we had these two half reactions here, and we wanted to describe and diagram a cell based upon them. So this particular thing should be on your practice worksheet. So notice, I hope this is alarming, or it's something you notice, that there's two reductions here. Remember, these are half reactions, so we can't have two reductions, meaning one of these things has to be flipped, because we can't have just two reductions happening. So we have to look at our table of reduction potentials, and we have to decide which one should be flipped. So instead of doing the sloppy writing, I'm going to show you. So if we look on our table of reduction potentials, I see this one, positive 80. I see this at positive 77, 0.77 rather. So again, I know that these two things, they cannot both be reductions. One of them has to be flipped. I have to have an oxidation and a reduction. I furthermore know that I want to keep the voltage positive, because only a positive voltage means a spontaneous reaction and a cell that will actually function, a galvanic cell that will function. So the one that I'm going to flip is the less positive one, which is this one. The logic behind that is, once I flip that one, that becomes negative 0.77, and when I sum them, they will still be positive, just barely. If I flipped the top reaction, then it wouldn't work, because the top reaction, if I flipped it, it would be negative 0.8, and when I added them, I would get negative 0.03. So it cannot be the top reaction I flip, it has to be the bottom one. So therefore, the two half reactions actually look like this, and the overall reaction would look like this. Yeah, that's what we'd have. Now, as far as the cell goes, oh boy, I got to try to draw a cell here. Got our one half cell here. Got our other half cell here. Got a random annoying line there. Got a silver piece of silver here. So this is Ag. And then we're going to have a piece of iron in the other half cell. That's Fe. We're going to connect it with a wire and with a salt bridge. And then in the silver cell, we're going to have silver ions, probably from silver nitrate. That's what we're going to put in there. And then in here, notice that this has both Fe2 plus and Fe3 plus ions in the overall reaction. I would want to mix, so this one's a little bit weird, but if there's any ions that are in the chemical reaction on either side, whether they're reactants or products, you want both of those ions in there. So I would need a mix of Fe2 plus and Fe3 plus ions, so maybe from some iron 2 chloride and iron 3 chloride, or iron 2 nitrate and iron 3 nitrate put into there. And then we need to think about anode and cathode. So oxidation at the anode, which is this one. So this is my anode here. And then reduction at the cathode. So this is my cathode here. This is my negative. And this is my positive. Clear as mud, right? Right. Yeah. Let's not do that one right now. All right. Well, you can try it. Yeah, try it. That's it for me, folks. Thanks for watching. Have a good day. We'll see you next time.